Swayam Prabha. Digital India. Educated India.
Okay, welcome everyone. So, we have so far studied optimization from a perspective of characterizing the solution of an optimization problem, but we have not considered the question of how does one compute such a solution. So, today what I will talk about is the basic ingredients of algorithms for computing solutions of optimization problems. Now, algorithmic development in optimization has happened ever since the ever since the subject itself was studied. So, there is a very long and varied history of this subject. So, we will not have the time to cover all such algorithms, but what I want to get a sense of are the various types of algorithms or the various flavors of algorithms that are classes of algorithms that are out there today, and the kind of ideas that underpin such classes of algorithms. The other thing I want you to get a flavor of is the kind of issues that arise in practical optimization algorithms. It is often very easy to think of algorithms as simply an iteration and analyze them simply on paper, but usually when one practically implements them, the kind of corner cases that come up require some special attention. So, I will shed some light on a few such practical issues also as part of this. So, in this module of our course, we will that is what we will be focusing on. So, to begin with, what I want to talk about is simply optimization without any constraints. So, we will be talking about what you would call unconstrained optimization or optimization over open sets, but for us for simplicity we will take the open set to be Rn. So, we will we would be looking at basically a function f that you would be looking to minimize over the entire space Rn, and we will assume that f is C1. So, it is continuously differentiable. Okay. Now, the simplest idea that you can potentially use is in optimization is what is called line search. Now, what is so before I tell you this particular idea, I should actually let us first get a sense of why optimization algorithms are a subtle matter, and why is it that these algorithms require why do we even need to be careful about how we think of algorithms. So, when we do analysis, when I draw a picture of the function like this on the board, something like this, I am effectively giving you the graph of f, and I am giving you at one glance how the function f looks over the entire domain. Now, this view is usually not present for an optimization algorithm. An optimization algorithm would work in a query mode. What does that mean? It would query the function for if it takes an x and queries, sends this as a query to f, and then what you have is a routine which will return you the value of f of x. So, it is possible to query the value of f of x and get it for any particular value, any candidate x that you pick. What you do not have is this kind of bird's eye view, where the entire graph is listed for you. Even if you wanted to construct it, what you would need is is the value of f for every possible x, and there are infinitely many such x's, right. So, the naive way for optimization is to approach for optimization is that you try and graph out the entire function to some degree of approximation. You cannot plot, you cannot evaluate it for every point. So, you say, well, let me evaluate it over a grid of points. Say there are, so you suppose you are evaluating it from 0 to 1, you make, let us say this is 0, this is 1. You are evaluating it from 0 to 1, you make a fine grid say of 100 points suppose, and evaluate the function at each of these points. Assume that there is that you can interpolate between the endpoints of the function or some such way, you create an approximation and then search over these points, over that approximation, or search over these points to get an approximate minimum answer. The trouble with doing this is that this works okay when the number of variables or the dimension n here is small, right. If the dimension n here becomes larger, then the number of points that you would have to make starts growing exponentially with n, right. So, if you are in 0 1 and you decide to make a grid of 100 points, you would need 100 points. A grid with where you subdivide 0 to 1 into if your accuracy level is 10 to the minus 2, then you would need 100 points. But if you are in 0 1 square, suddenly you would need 100 square 0 1 cross 0 1, then suddenly you would need 100 square points. And more generally, if you are in 0 1 to the n, you would need 100 to the n points. So, you can see this sort of approach to optimization where you do what you would have what you were attempting to do on paper, which is simply graph out the entire function over the function over the entire space and try to compute the value of the function on a grid of points, and then from there evaluate, basically just list out the values and pick out the least possible value. This kind of approach is not feasible computationally at all, because when the dimension becomes larger, it is today considered the approach of last resort. Essentially, you would not want to do this as and if you have any better option, right, because the number of function evaluations you need is ridiculously large. Second, this is one. So, in addition to this, there is also the fact that you have not made any use of any of the theory that we have developed about optimization, right. We have developed KKT conditions, we have developed conditions for a function to be a minimum and so on. This way of graphing the function and then simply selecting the least point makes no use of any of that. So, it's actually it shows you how generic this is and how and as a result how potentially inefficient that it could be, because there are many more things that you can make use of which you have ignored in this approach. So, what we would the approach that we will take is that of search. So, what does search mean? By search I mean that we start out at some point and then we query the function. The query reports back to us the value of the function. In some cases it may report back to us more. You could ask not just for the value of the function, but you could also ask for, say, the derivative of the function, the Hessian of the function, or some or any other such information about the function. Depends on what kind of properties you have and what are you allowed to query. Now, suppose you are so what we will do is you start out at a point, you query the function to get these vital stats about the function, its value, its derivative, etc. Then from there make an educated guess about where you should be going. Okay. You started out at this point, which is kind of arbitrary to begin with, but then based on the information that you have got about the function and its derivative, you get a sense of where you should next go. What does that mean? You try to create, using this information, a model of the function around this point. So, you could try to create a model of the function in a neighborhood of this point. And then we say, okay, well, now based on this model, what should I be doing? And that, based on that, you select the next point. And the next point, and then having selected the next point, you again query the function at that point. You get values of the function and its derivative at that point, and you create a new model. You create a new model and then decide where you should next go. Okay. Now, when I say we create a model and so on, these are not very complicated models. Usually, what we are saying is we are using some sort of a heuristic which says that we will be moving, say for example, along the linear approximation to the function. Right? We take the function to be equal to its linear approximation. That is our model, and then we move in that direction, and then then we move a step further in that direction, revise our model, move a step further, and so on. Now, every such approach will be only as good as the model. So, we cannot obviously trust our model too much. So, we would want to so therefore, this kind of an approach works in baby steps. You start from a point, you have a model, say for example, you take a linear approximation, you trust that model to work in a certain neighborhood. So, you take a step that is not too large within using this particular model, reach a new point, and then revise the model, and then take another step, and so on. So, this leads us to an iteration that and what we want is that the limiting point of this iteration, the limit as the number of iterates goes to infinity of this particular iteration, converges to the minimum of the function. So, this is the mathematical property that we are looking for. So, what one looks for is that that these iterations end up verifying at least the necessary conditions of optimality. So, it should satisfy all the necessary conditions of optimality that you can say about this particular function class that you are considering. So, for example, if the function class is a differentiable function, then we would want that this sequence of iterations, say xk, we would want that this sequence of iterations converges to an x star such that gradient of f at x star is equal to 0, right. So, this is the flavor of results that we are looking for, all right. Okay. So, the first type of algorithm of this kind, of this category, is what are called line search. As I mentioned here, line search. Now, what is line search? So, line search essentially does the following, that it looks at this looks at an optimization problem of this kind. So, you are minimizing a function f over the entire space x in Rn. It starts out at a current iterate xk, and then updates xk by looking at how the function behaves along the direction along a linear approximation, where the linear approximation is obtained by using the gradient of the function, right. So, let us define. So, let me erase this and let us define the following. So, define phi of alpha as f of xk plus alpha times pk, where alpha is is greater than 0. So, let me explain what each of these terms are. So, xk here is your current iterate, okay, current iterate or estimate of the minimum. Pk is a Pk is a direction in which we will search for a better iterate. Now, alpha here, this is what we call step size. Okay. What is this step size? Step size tells you the extent or the distance or the you would like to travel along this direction Pk to get to the next iterate. Okay. So, alpha, the step size, is what does it capture? It captures the extent to which you travel from xk in direction Pk to get xk plus 1. All right. Okay. So, what we have done is we have parameterized the next iterate by this step size, and the entire idea of line search is to pick the right step size and the right direction. Okay. All right. So, let us take this one step forward now. Okay. So, a typical line search algorithms, what they would do is they would keep trying out values of alpha. So, okay, so before I tell you that, let us actually see what we would want to do. So, suppose you are suppose we have a function, this sort of function, and suppose you are at a point like this. And this is the direction. This is the direction Pk that you have. We are at a point xk here. This is, and Pk is the direction pointing to the right. Now, what you would like to do is travel starting from xk. You want to travel in the direction Pk, and the question you are faced with is how much should I do? How much should I travel? So, you could could say, well, let me go. So, remember Pk is simply a direction. So, there is no scale to Pk. So, you have to actually define the scale and the extent to which you want to travel in that direction using the term alpha, right. So, suppose you move until here, say, okay. Suppose you move until here. Now, until here you are getting actually a decrease in the function, right. Now, you could and you could stop here and say, well, okay, I have got enough decrease and then revise the model, or you could say, well, I have got so much decrease, everything looks great, let me move further. You go till here, you could take or iterate all the way till here, and then you see, okay, well, my decrease hasn't started hasn't kept up. Maybe I should now revise my model and get to a new point. Or you might say, well, no, okay, let us give it a try. Let's increase alpha further and see if that works. And then the function starts increasing, and then you end up with somewhere here. So, you can see what is happening here is that there are if as you go from in this entire range of alphas, you encounter various types of situations. You encounter situations where it seems like your decrease is you have made a decrease, but the function could decrease further. You could get to a situation where you have made a decrease, but the function cannot decrease. You do not think the function can decrease any further in this direction. you get to a you could also get to a situation where you have overcompensated. You have gone to you've taken too large a step, and you haven't really got the decrease that you think you should have got. For example, if you take a decrease if you take a very large step, you could end up here, and you end up actually missing what could have potentially been a solution here also, right. So, now the problem is there are infinitely many alphas to choose from, and there is, since we do not have the graph of the function, the only way we can go about selecting the alpha is through some sort of intelligent trial and error. You might try this, you might try that, etc., etc., and then you realize you need to get you have to sort of feel your way through and figure out what the correct amount of alpha should be.